In this talk I'll present our recent results on magnetic field decay in neutron stars. I'll start with some introduction, then remind our previous results on the subject, and finally present our recent results which I just submitted. From observations we know that there is a big diversity of young neutron stars of different kinds, from standard radio pulsars, which are most numerous among known objects, and up to magnetars, antimagnetars, and other types of neutron stars, which are less numerous in terms of known sources. However, if we calculate their birth rate, we see that objects like central compact objects or magnetars or the Magnificent Seven contribute a lot to the total budget of neutron star formation rate. The origin of this diversity of observational appearance and physical properties of young neutron stars is not completely understood, and the goal is to make a so-called model of grand unification for neutron stars to explain this diversity in the same framework. Many attempts have been made during last, say, 10 years, and probably the main ingredients of these unified models are related to magnetic fields of neutron stars. So we can discuss field decay, emergent magnetic field, and diversity of magnetic field topology. So all these subjects are actively studied now, and there are lots of new observations, lots of new theoretical approaches, theoretical models. Here we'll speak mostly about magnetic field decay. If the magnetic field is constant, then in the P-Pdot diagram, a neutron star evolves along such a track shown with the straight lines, and probably as a zero approximation, it works for standard radio pulsars with fields around 10 to 12 Gauss. However, obviously it is not working for magnetars, and then tracks might be much different. So we start with large fields, large spin down rates, and then rapidly, in say less than 10 to 5 years, these fields decay significantly. We see different astrophysical manifestations of magnetars related to the dissipation of energy of their magnetic fields. And we don't know well what happens when magnetic field of such neutron stars decays down, say, to 10 to 13 Gauss, maybe if it continues to decay, or the decay saturates around this value, around 10 to 13 Gauss, at least by an order of magnitude. Maybe this rapid decay saturates because of the stage of so-called Hall attractor, which was recently, say 5 years ago, proposed by Gorguliatas and Cumming. And from the observational point of view, there are different indirect indications that this stage is necessary. However, there are no direct proofs that this stage is there. Still, this is a very tempting idea that after several Hall timescales, very rapid reconfiguration of magnetic field in the crust of neutron stars stops, the field reaches some equilibrium state, and this significantly slows down the magnetic field decay. There are many approaches to estimate characteristic timescales of the magnetic field evolution, and we can discuss three main processes. The Hall cascade. This process is not a dissipative one, so we are dealing just with reconfiguration of the magnetic field, but what is important is that the topology of magnetic field evolves in such a way that the characteristic scale, spatial scale, will become smaller, and as you see, the ohmic dissipation time scale is proportional to this spatial scale in the power 2. And so if we have smaller loops, say, of the magnetic field, then the dissipation produces much faster. And so the whole cascade is important in this sense, that there might be some very rapid process of real dissipation, some ohmic process, but it's necessary to drive the characteristic scale of the magnetic field down to smaller values. As for the ohmic processes, we can divide it in two parts. In one, we have scattering of electrons of phonons in the crust, and the second process is related to scattering of electrons on crystal impurities in the crust. So for brevity, I'll call them phonons and impurities to distinguish between them. The scale of magnetic field decay due to impurities is related just to properties of the crust, and it's typically parameterized with this parameter Q. And decay due to phonons is temperature dependent, and you see here temperature in the denominator, and thus it is more important for young hot neutron stars and less important for mature neutron stars when they cool down. All this approach is carefully and very well described in the paper by Cumming and his collaborators 2004. So what about observations? In principle, if we analyze the whole population of radio pulsars, it seems that it is not necessary to introduce magnetic field decay, which operates in exponential manner with the same time scale during the whole radio pulsar evolution. Of course, if you add this option, all fits becomes better in population synthesis, but in principle there are several papers in which, especially for normal radio pulsars, this is not necessary. However, there are indications that there are episodes in the lifetime of radio pulsars, especially when they are relatively young, when significant field decay is probably visible. So we studied it 6 years ago in this paper, and we studied neutron stars with ages, say, from roughly 10 to 5 up to 10 to 6 years. We analyzed two big sets of data, and we found that in this interval of real ages, the magnetic field decays by a factor of roughly 2, and the characteristic time scale is about 400 kiloyears. However, it is impossible to continue with the same rate of magnetic field decay further, because then we'll come to contradiction with the observational data. Magnetic field decay is too fast, so we have to make a physical model in which, on one hand, we have relatively rapid field decay for normal radio pulsars during this period of time, but then we have to switch off this rapid decay. And so our next step was to form such a model. We have to model whole process, ohmic dissipation due to impurities and phonons, and the last one is temperature dependent. So we took calculations of neutron stars cooling made by Peter Sternin and his collaborators in St. Petersburg. We made analytical fits for this temperature. I have to underline that here we're dealing not with the surface temperature, but in the temperature in the crust, say with the temperature below the heat blanket in the outer layers of neutron stars. So typical values are 10 to 8 Kelvin, which roughly corresponds to surface temperature about 10 to 6 Kelvin. So we made several tries, including all three types of magnetic field evolution, whole phonons and impurities, and then switching them off one by one or modifying them. Of course, you cannot completely switch off impurities, but you can modify the parameter Q. We used the differential equation proposed by Aguilera, Pons, and collaborators in 2008 to calculate this evolution. And what we obtained is visible here, and I presented these results 5 years ago in one of the previous conferences of this cycle. And we see that at some moment we switch off the whole process because of the Hall attractor, and we actually in this model we switched off field dissipation due to electron scattering of phonons, and this corresponds to this time scale. So here this feature in the red curve, for example, it's more visible, and these clear features after which we have only field decay due to impurities. So we can feed parameters to explain findings we got from the data. We can feed to explain it either with phonons or with Hall cascade. So both are possible, maybe both of them contribute, and this is the equation for field evolution. This is the analytical solution again from Aguilera and collaborators. And we tried to go a little bit deeper, trying to distinguish between Hall process and phonons. So our method is sensitive to ages about several hundred kiloyears here. And that's the moment at which the critical temperature at which we switched phonons is reached. So here it's clearly visible. So if we use such an approach, we came to the conclusion that it is easier to switch off the rapid magnetic field decay in proper time if we are dealing mainly with phonons. So whole process probably is less important in young normal radio pulsars. However, now we can make a step further, and that's what I want to present in the third final part of my talk. Recently, a big group of authors presented a very detailed pulsar timing of a big sample, close to 100 pulsars, and for many of them breaking indices are measured, and we analyzed different approaches to explain the data these authors obtained. And these are their results. So I remind what is the breaking index. It's a combination of the first and second period of frequency derivative. We are working in a relatively simple approach with a slightly modified classical magnetodipole formula. And in this plot, you see in red measured values of the breaking index, and in blue upper limits. So we are dealing only with this part, with these red symbols. I have to note that already in these papers, the authors discussed, of course, some possibilities to explain these breaking indices significantly different from the classical value 3. So from classical magnetodipole formula, we get 3. And here typical values are several tens, which is a little bit puzzling. So let me show in the P-Pdot diagram how a neutron star evolves with different breaking indices. This is from the paper with the data, and here just a nice plot from another paper by different authors, which clearly shows the direction of evolution for different breaking indices. and these blue lines corresponds to n equal 3. So if we have n larger than 3, this can be an indication of decaying magnetic field. Of course, other processes also can be in work, also unrelated to a neutron star itself. For example, it can be a member of a binary, so orbital motion can contribute to timing, and if you don't take it properly into account, you have a, say, fake value of the breaking index. We also discuss these options and come to the conclusion that the magnetic field decay is the best option, and now I present these results. So we upgraded our model of magnetic field decay. Again, we include the whole process, whole cascade, whole attractor, ohmic dissipation due to phonons and due to impurities. And we calculate this field evolution for different masses of neutron stars, because thermal evolution depends on the neutron star mass. So for the time scale of magnetic field decay due to phonons, we use this approximation. It depends on the temperature, so we take cooling curves, and there is a constant related to internal properties which corresponds to the, say, initial time scale of decay due to phonons. And if we take a typical mass of a neutron star, you see on the left plot the magnetic field evolution, and on the right the evolution of the breaking index depending on the characteristic age. Here we plot n and characteristic age because both are measured properties. This on the left we plot, say, physical properties, and on the right measured properties. And you see that in principle you can fit large breaking indices with these parameters. However, you can do even better if you take lighter neutron stars. Obviously, if a neutron star is lighter, then in most of scenarios its internal temperature is higher. Higher temperature, smaller is the time scale for the magnetic field decay due to phonons. If you have larger you have more intensive magnetic field decay. If you have smaller time scale, then you have larger breaking indices. And this is shown in the right panel of this plot. Now you see that we can easily fit with realistic parameters these large breaking indices up to 100. If we take neutron stars with masses, say, 1.1, we have to underline here that this value of mass, which fits the observational data, significantly depends on the equation of state, on the exact cooling curves, and of course for a different model it might be different. So in principle it is possible to look for a model of thermal evolution which can allow to fit this data not with 1.1 but, say, with 1.2 or maybe even with large neutron star masses. So there is a room for more refined fitting, but it's not the scope of this work which I'm presenting, because our idea was to demonstrate that the magnetic field decay due to phonons for realistic parameters can explain also this recent data on large breaking indices of many radio pulsars, many young radio pulsars. So here I come to my conclusions. So we used advanced version of our model of magnetic field decay to analyze recent data presented early this year on radio pulsar timing, on breaking indices of these objects, and we demonstrate that magnetic field decay due to phonons can nicely explain this data for realistic parameters. Thank you.